I'm very pleased to introduce our science speaker tonight, Dr. Charli Sakari. Dr. Sakari is an assistant professor in the astronomy department at San Francisco State University. She completed a PhD at the University of Victoria in British Columbia, Canada, and then went on to a postdoctoral research position at the University of Washington in Seattle before joining San Francisco State. Dr. Sakari's research covers chemical abundances of stars in globular clusters, and tonight she's going to be talking to us about using these stars to probe heavy element formation in the early universe.
All right, thank you, John. So thank you all for coming to the second showing of this talk. So indeed, I'm Charli Sakari from San Francisco State. And before I dive into talking about research, I want to first give a shout out to my wonderful research group at San Francisco State. We have undergraduate and master's students there. Here is most of us in a Zoom call in fall 2020. Since then, several students have moved on to PhD programs or jobs in industry, and others have joined our research group. I'm not going to have time today to talk about all the work they're doing, but I am going to highlight some of the wonderful work they're doing. If you're interested and would like to know more, please do ask. They are doing a lot of really great things. So what I'm going to talk to you about today is I'm going to talk to you first about sort of what chemical abundances are, how we figure out this information about stars, and why that's useful. So an overview of all of that. Then we're going to focus in on two specific elements. Barium, you've probably heard of the element barium before, and one you may not have heard about called europium. And we're going to talk about how those elements are created. This is in a process called the rapid neutron capture process. We'll talk about what that means. I'll then talk about a collaboration that I'm part of called the R-Process Alliance. And we'll talk about the work that we're doing at San Francisco State. Then I'm going to have a bit of a digression and talk about globular star clusters and how they're connected to the R process. And I'll give you a bit of an intro to them, and we'll talk about the work we're doing at San Francisco State. And then at the end, we'll talk a bit about our place in the universe. All right, so we'll start out big with our overall goal of this research, which is to understand the universe. So the goal of a lot of astronomy. So this is kind of a timeline for what we think our universe has undergone over the past 14 billion years. So we start out with the Big Bang that created our universe. We have these early periods of the first formation of the first elements, the formation of the first stars and galaxies. Then we have this period of time where stars evolve and die, new stars form and evolve and die, galaxies merge and create bigger galaxies, and the universe evolves to today, about 14 billion years after the Big Bang, where we see all the wonderful things in the universe around us. And so really, we'd like to understand a lot about this. We want to understand, why do the things we see around us behave the way they do? How were they created? How have they changed? How is this like other objects in the universe? And ultimately, what is the physics that underlies our universe? And so there's a couple different ways that we can get at answering this question. And so I am an observer, so I like to actually look at the stars and in galaxies and understand what they're doing. And so observationally, we can think about understanding the universe in a couple different ways. And one of them, if we want to understand the early stages of the universe, is to actually try and observe these first stars and galaxies. And so that's something that JWST is doing, for instance. JWST can see objects that are really far away. They're so far away that their light has taken a really long time to reach us. And so we're seeing them when they were very young. And so JWST is going to be able to see some of the earliest objects that formed in the universe. I, however, do something opposite to that. So instead of looking for things that are very young, I look at things that are very old. And I use these old objects to understand things that have happened in the past. And this is commonly referred to as galactic archaeology. So one of my master's students likes to say it's like Indiana Jones, but in space. And so this is where we use old objects, old stars, to understand things that have happened in the past. So similar to how archaeologists, dig up artifacts and then use them to understand the civilizations from the past. So it's the same kind of idea. And so I am particularly interested, as John said, in the chemical compositions of the stars. And to understand why, let's think about how stars form and evolve over time. And so this is a nice cartoon from NASA that kind of shows all of this in one go. And so we start here in the center in this star-forming nebula, or star-forming region. And this is a cloud of gas and dust. And so stars form sort of mysteriously in these nebulae. And the types of stars that form, we typically classify them based on their mass. So a star like our sun, we would call a low-mass star. And that's different from a high-mass star, which has maybe 8 to 10 times more mass than the sun. And so these different types of stars have different evolutionary paths. So they grow and evolve differently. So a star like the sun will, exist for billions of years, like the sun we see now. And then eventually it will become what we call a red giant. And when it becomes a red giant, it blows up and becomes much bigger and redder. And then eventually after that, it will become a planetary nebula. And planetary nebulae have nothing to do with planets. They are just named that because when early astronomers looked at them in telescopes, they kind of looked like planets, but they are not planets. And so during this planetary nebula phase, the star kind of blows off its outer layers and reveals, left behind, the former core of the star, which in this case is a white dwarf. But the winds that it blows off, it actually can blow off into a new nebula, not the same one, but a new nebula, and make new gas and dust, and so new stars can form out of that material. So a similar cycle happens on the other side. Massive stars, they actually evolve much more quickly than low-mass stars. They burn through their fuel faster. Then they enter this phase called the supergiant phase, where they can have strong winds and they can blow off the material from their surface. And then they will enter the end stage, this massive supernova explosion, where they project a lot of material off in this massive explosion and leave behind either a neutron star or a black hole. Similar to the low-mass star, during these winds or the supernova explosion, they blow off material, which can then go into a new nebula and new stars can be formed out of that material. So that's why these are showing these cycles, right? Because this is sort of an ongoing process, right? As a star evolves and dies, it creates material that goes into forming the next cycle of stars. It's the circle of life. So what's cool about this is that as these stars are going through their lifetimes, they're actually creating new elements. And this is a process that we call nucleosynthesis, the creation of the elements. And so, for instance, our sun, in its core, is taking hydrogen and making helium out of it. And that's how it's creating energy. The light that we see from the sun is created during that process of fusion. And as the sun will go through the rest of its lifetime, it will create other elements in other processes. And some of those elements will be in the winds that are blown off of the star, and those elements will then make it into the star-forming region to create new stars. So what this means is that over time, the new generations of stars are increasingly more enriched in those elements that are created by previous stars. So it continues on in a cycle and getting more and more enriched. So if we see an old star, so take the sun is like 5 billion years old. If we see a 5 billion-year-old star like the sun, its current chemical composition, the elements that it's made of now, are actually going to reflect its birth environment, the nebula that it formed out of, even though it's far, far away from where it formed. And remember, I showed with that previous cartoon that the composition of that star depends on the generations of stars that came before it. So this means that we can look at these old stars and we can use their chemical compositions now to understand the generations of stars that existed in the past. And so that's really what we're getting at when we're talking about galactic archaeology. All right, so what do I mean when I say chemical composition? Don't worry, it's not too complicated of chemistry. Instead, you may have seen this before. This is the astronomer's periodic table. So we have hydrogen, helium, and everything else we call metals. There are some reasons for this, some good, some bad. But really, I guess the main reason is because in the very early universe, we have this period of what we call Big Bang nucleosynthesis, where we create a lot of hydrogen, some helium, and then trace amounts of elements like lithium. But most of the elements in the periodic table were actually created in stars. And so that's part of the reason why they can be sort of lumped together as metals. I actually care, however, about the elements that are part of the metals here. So here's another periodic table, and this is now color-coded by Jennifer Johnson to show the different astrophysical sites, so the places, the types of stars that create these elements. And we're going to break this down in just a bit and go into more detail. But what we should take away at this point is that this is a colorful periodic table. There's a lot of different places these elements can form, a lot of different pathways. And so there's a lot of information. If we can determine these elements in every star, we can get a lot of information about the types of stars that existed before this star. So how do we get this information? Well, it would be nice if we could go to the star and take a sample and, actually analyze it in the lab or something. But we can't do that, right? All we have to work with, for the most part, is the light from the stars. And so we have to get creative with how we work with the light. And so what we can do in this case is we can take the light and we can spread it out into a spectrum. And so in this famous album cover, we see the process illustrated, that the light that comes in here, it looks to be white, but when we take it out and spread it out through this prism, we see all the colors of the rainbow. And so that's essentially what goes on when we're taking a spectrum, and the process of taking the spectrum we call spectroscopy. And so if you were to do a similar sort of thing, at your house, take a prism, take the sunlight, spread it out, you would probably see exactly that, a rainbow spectrum. However, if you use the high quality spectrographs that we have here at Lick Observatory, for instance, you can actually see more detail in that spectrum. And you'll see something like this, which is the rainbow spectrum, but then on top of it are these dark bands, which we call absorption lines. And these dark bands are the result of atoms in the atmospheres of the stars. So to understand why, we'll look at this terrible graphic that I made that's very much not to scale. And we'll imagine that we have a huge telescope on Earth that's looking at this star in space. And if we had something like, a perfect light bulb in space, we would imagine that, okay, we would expect to see something like a rainbow. But that's not quite what's happening with our stars. Instead, our stars have this atmosphere surrounding them. So it's sort of similar to Earth's atmosphere, but of course, you can't breathe it, and you would die. You would be incinerated because it's very hot. But it's the same sort of idea, right? It's like a thinner layer that is different than the denser, more opaque layer beneath it. And so as light is created down here, it makes its way through the star, and it finally thinks it can escape, but it still has to go through the atmosphere. And as it does that, it encounters atoms that are in the atmosphere. And for the most part, those atoms, because I said it's thinner, they're more dispersed, for the most part, they don't care so much about the light that's coming out. However, they do care if that light has a specific energy or color. And if the light has a very specific energy, the atoms can absorb that light. And when they absorb that light, we see it missing from the rainbow spectrum that we get back on Earth. And the specific energies that are removed actually change depending on which element you're looking at. So when we see an absorption spectrum like this, we can focus in on specific lines, like say this one, or this one, or this one. And we could say, okay, this comes from sodium, this comes from hydrogen, this comes from calcium. And the more atoms that are present in the atmosphere, the more light is removed. So the darker the line, the more of that element there is. And so this means that we can use absorption spectra like this to figure out which elements are present in the atmosphere and how much of them there are. So I typically look at spectra like this. And unfortunately, instead of looking at pretty rainbow images, I look at them like this, which is still beautiful. And so here what we're seeing is a spectrum of the sun, and it's a very, very high quality spectrum, and it's just a very tiny, tiny region of this rainbow spectrum. So it's, you know, somewhere here in the orange area. And what we see on the x-axis here is the wavelength or color or energy. And so this is sort of like a yellow-orange side over here. This is a slightly redder orange over here. And then on this axis, it's showing the brightness. And what I've done here is I've set this level 1 here to be where the rainbow continuum would be. So that's where the rainbow is. And then each dip we see here is where we're missing light. So that's where there's those darker absorption lines. And I've labeled several of them depending on which element they come from. And so you could see, you know, here's a nice barium line, here's a nice calcium line. And so in this high quality spectrum, even just this small portion, we see a bunch of different elements, including some like vanadium that you've probably not really heard of before. And recall, each of these elements forms in a different place, different time, you know, has maybe different ratios of the processes that create it. So a spectrum like this can give us a lot of information about the types of stars that existed before the star we're looking at. All right, so that was our overview. Hopefully you're still awake. And so now we're going to focus in on two specific elements, barium and europium. So before we talk about them, let's return to this periodic table. And one thing I think you could probably just notice immediately is that there's a bit of a color change about halfway through, where we go from having this blue-green scale to this orange and yellow scale. And this is because we end up having a slight difference in how the elements are made. So if we're looking at elements like oxygen or magnesium or silicon or calcium, those, oh, we have a question?
How come at the bottom this PM is gray?
Sorry, which part? Oh, gray. Oh, yes, thank you. That is a good question. Let me come back to that in just a moment. Yes. Actually, oh no, I'll just do it now, or I'll forget. Gray is because they actually don't exist for very long because they decay very quickly. And so they're gray because we wouldn't actually observe them in stars. So they have a very short half-life, is what we'd say. And so they're gray here to show that we wouldn't see them in typical stars. Yeah, thank you for that. So elements like magnesium or silicon or calcium, they typically form through fusion. So fusion is where, you know, you have two elements and you slam them together to make a new element. So that's what's happening in the center of the sun when we're taking hydrogen and making helium. It's really hard to do that, actually. You know, we can't do it on Earth yet. We need stars to be able to do it. And it's even harder to do when you have more and more and more protons. So the number of the element is given by the number of protons it has. And so as you get to these heavier and heavier elements, they have more and more protons. Protons have a positive charge, and so it's harder to bring two positively charged things together. It gets harder and harder the heavier the element. So we can't make these elements through fusion. And so that's kind of some of what we see in this color difference here, is that we can't make these elements through fusion. So how can we make them then? Well, we need another process. And in this case, it's called the neutron capture process. And so this is where I mentioned it's harder to bring protons together, but a neutron has no charge. It's neutral. which is where the name neutron comes from. And so it doesn't have that problem. It can actually go into the nucleus and stick there, no problem. And so this video is going to show this process, and it's just meant to illustrate the general process. This is a video from a professor at the University of Oregon, and what we see here is a nucleus, and it has so many protons and so many neutrons. The protons are red, neutrons are blue. And remember that the proton number dictates what element we're looking at, so here we have nickel, element 28. And so what we'll see in this video is that we can take neutrons and we can shoot them at the nucleus, and they can go in and stick there, and our neutron number increases. But this actually is not very stable, and the nucleus doesn't like it, and so we see that one of those neutrons is going to decay into a proton. And in doing so, it actually creates a few other particles as well. And what you see when it turns red is that the proton number increases. So it will go up to 29, which is copper. So this is how we're able to create those heavier elements in the periodic table, is through this neutron capture process. And the types of elements that we create in this process depend on really the rate at which we throw neutrons at it relative to that decay timescale. And so we have sort of these two main processes that I'll talk about tonight. If we do that slowly, so we slowly put the neutrons in, that's the S process. And rapidly, if we do it rapidly, that's the R process. Easy to remember. All right, so if we go back here, so instead of these are the astrophysical sites that we think are where these objects form. I'm instead going to code them by the R process and the S process. And a very astute audience member from the first session noticed that these are yellow as well. These are not really necessarily S process, so we'll just, this isn't suitable for that. But anyway, we'll focus on these heavier elements here. So orange is the R process, yellow is the S process. And what we see, these heaviest elements that are shown here in the periodic table, they are only orange, only R process. And that's because we need that rapid flux of neutrons to be able to make them. So now let's focus in on the two that we're interested in for tonight, barium and europium. So we see that both of them can form in both the R process and the S process, but barium is mostly yellow, so that means it mostly forms in the S process, whereas europium is mostly orange, so that means it mostly forms in the R process. And these elements are relatively easy to see spectral lines from them in the stars that we're looking at. And so we can then use, the ratio of how much barium we see relative to europium to tell us whether we see signs of the S process or the R process. All right. And so here were the astrophysical sites that were listed for these two stars. And so barium, the S process is listed as dying low mass stars. So this is, at the end stage of a star like the sun, or slightly more massive than the sun. It will go through this period called the asymptotic giant branch phase. And when it does that, it can create the S process. The R process, on the other hand, is listed here as coming from merging neutron stars. And I put this question mark here, which we'll talk about in a minute, because there's a question as to whether it's the only source of the R process. But you may remember from that cartoon of stellar evolution that neutron stars come from predominantly massive stars. And so we see massive stars here, low mass stars here. We have a bit of a difference between the sites of the S process and the R process. All right, so now back to the creation of the R process. So prior to 2017, these were sort of the two main theoretical sites for our process. So this is the one that was listed on the previous page, the neutron star mergers. Oh, these are both artist interpretations. These are not real images. I want to point that out. And so a neutron star merger is exactly what it sounds like. It's the merger of two neutron stars. And then this one is sort of an exotic type of supernova called a jet supernovae, which is thought to happen when you have a very magnetic star. So this was, prior to 2017, these were the two main theoretical sites. And then in 2017, we had a very exciting event. LIGO, the Laser Interferometer for Gravitational Wave Observatory, detected a neutron star merger through gravitational waves. And we were then able to, get observations of it through follow-up observations, and we saw that neutron star mergers can indeed create the R process. So this is definitely a site. This is still a question as to whether it is an actual site or not. But both of these do require massive stars to create the R process. So now I want to talk about how barium and europium actually change over time in the universe as a whole. And so this is a process that we call chemical evolution. And so let's start in the early universe. So remember that in the early universe, we have no barium and no europium. In that period of Big Bang nucleosynthesis that I mentioned, we create hydrogen, some helium, and trace amounts of things like lithium or beryllium. But we have no barium or europium. All the barium and europium in the universe is created by stars in the S process or the R process. After the first stars form, the massive stars evolve fastest, and they can create barium and europium through the R process. So at that point, we can have the R process start to increase throughout the universe as those stars create it. The lower mass stars take longer to evolve to that stage. So after those low mass stars evolve enough, eventually they can create the S process and make a lot of barium but little europium, and the amount of S process in the universe goes up. So this period of time here, before we have the S process, is a really great place to look to study the R process. For me, the S process is annoying, right? It's like a contamination. You don't want it there if you're looking to study the R process. This is also an interesting time in the universe, right? It's when the first stars formed, just after those first stars formed. And there's a lot of interesting questions. Can neutron star mergers even happen early enough to create those elements that early? Are there enough of them in the universe? If we see our process elements throughout the universe, can that be explained by neutron star mergers alone? And so this is a really interesting period of time to look at. So we want to find stars that formed during that time, or as close as we can to that time. So how do we do that? Well, recall that in addition to there being no barium or europium in the early universe, there was also no iron, no calcium, none of those other elements, right? Those are also created in stars. So after the first stars form and evolve and die, they make a bit of iron, calcium, all the other elements, etc. Subsequent generations make even more. And so the amount of iron in particular in the universe goes up over time. So if we want to find the earliest stars from this period of time, we want to look for stars that have the least amount of iron we can find. And those are what we call the metal poor stars. So we say metal poor because they're sort of lacking all of the elements together. That's again thinking back to the astronomer's periodic table. So there's a little bit of a problem with this, because if they're iron poor, they're also going to be our process poor. And that means that we might get a spectrum that looks like this. So this is a spectrum this is a spectral line here, and this line is showing where we expect a spectral line from the element europium. We need there to be a spectral line there to be able to measure the strength of the line and figure out how much europium there is in the star. But there isn't really anything there in this sort of typical star, what a collaborator of mine would call a vanilla star. However, if we take the amount of europium relative to iron and we increase it, we see that we get a nice europium line that pops out. And if we increase it even more, the line becomes even stronger. And these, we can easily measure the strengths of those lines. We can easily get europium abundances in those stars. So we call these, the R1 and R2, these are classifications to mean that a star is moderately enhanced or highly enhanced in europium. And just as a reminder, we need this enhanced europium to be able to see these spectral lines. So all this is to say that if we want to study that interesting period of time and we want to study the R process, we need this type of star that we call an R process enhanced metal poor star. And we also want to look at barium as well because we really want to make sure we don't have any signs of the S process because it's annoying. All right, so we're looking for this sort of really interesting type of star, the R process enhanced metal poor stars. But before about 2018, very few of these stars were known, especially in this highly enhanced R2 category. And finding more of these stars was a primary goal of this collaboration that I am a part of called the R Process Alliance. And this is showing the core members of this collaboration. We are all observers, and our immediate goal was to find more of these stars, figure out, where they are and where they came from, and use this information to understand more about the R process. So when it comes to finding more of these stars that we can get this information for, it's actually really hard to find them, right? There's a lot of stars in the universe, a lot of stars we can see with our naked eye, even more that we can see with telescopes. And metal poor stars are rare. Our process enhanced stars are even more rare. So how do we find them? Well, if we're wanting to do a survey, we don't want to waste our time looking at sort of normal stars like the sun, right? We want to specifically target metal poor stars. So our first step is to identify metal poor stars from large surveys. There's a lot of large surveys that are observing, hundreds of thousands or millions of stars. And so this is the work from a lot of my colleagues, but also some of my students are doing this work. So Dilpreet Kaur has been working on this for her master's thesis, looking at some of the metal poor stars in the Apogee survey. Some of my undergraduates, current and former, have been looking for metal poor stars in another survey called GALA. And these are great places to find these stars. And once we find candidate metal poor stars, we want to actually go and get spectra from them. So for instance, using the telescopes here at Lick Observatory. And we then want to get those nice high quality spectra so we can measure those spectral lines from barium and europium and get that R process classification. And again, some of this follow-up is where we are doing at Lick using the Shane telescope, the 3-meter that's further down the road. So I'm not going to have time to talk about all of the work that we can do with this data, but the R Process Alliance has doubled or even tripled the number of the R1 and R2 stars that we know about. And we can do a lot of really interesting things with this data. And so here's just a few examples. So this plot is going to show the patterns of elements. So we can actually get more than just barium and europium. We can get a wide variety of elements. And so this is showing the abundance, which is the amount of an element, versus atomic number. And so remember, atomic number is the number of protons that an element has. And so for reference, here's barium and europium, the two elements we've been talking about. Here are the patterns of these elements in the sun. And so we've broken this up here. The solid line is the R process, the dashed line is the S process. So this is what we see in the sun. And what is really phenomenal about this, or amazing about this, is when we look at metal poor stars, they agree by and large with the solar R process pattern. And so these are 3 stars that I've plotted here. And then this is one star showing the difference between that star and the sun, the solar pattern. And some of these stars have as much as 1,000th, 1/1000th the amount of iron that the sun has. So that's pretty metal poor, much less iron than the sun has. But yet they have the same pattern of elements. And this suggests that wherever the R process happens, that it creates the same numbers of elements in the same ratios every single time. And this is really hard for models to be able to do. And so this is also an interesting question. Can neutron star mergers do this? probably is the answer, but it's remarkable that this agreement happens. And so some of my students are looking at patterns for more of these stars. So master student Jessica Agnos is looking at patterns for 3 more stars. These stars look like they came, that they actually originated in dwarf galaxies that have fallen into the Milky Way. And she's being assisted by undergraduate Pedro Silva to look at these 3 stars. Another student, Hamza Khan, is looking at the patterns for another type of star that we call a limited R star. And that's a star that's enhanced in these lighter elements, but seems relatively normal in these ones. And he is also looking at the patterns that we see here. And so this is interesting. We can compare these with models to see, what the likely sites were for creating these abundances. Another thing we can do is ask, where did these stars come from? And so this is an artist's conception of the Milky Way. And it is showing, here's what we normally think of as the Milky Way, a nice spiral galaxy. And what we see here is a dwarf galaxy that is orbiting around the Milky Way. And as it's orbiting, it's being shredded, and that's what we see as these streams that wrap around the Milky Way. And we actually see these streams when we look in the sky. This is a real image from the Sloan Digital Sky Survey that's been sort of color-coded here to show these actual streams that we see in the sky. And so this shows that the Milky Way is actively eating up these dwarf galaxies that are in the outer regions. And so as these stars are sort of gobbled up into the Milky Way, they're initially part of these streams, but over time they kind of dissipate and they look just like normal Milky Way stars. And a lot of work that our collaboration has done has shown that many of these highly R process enhanced stars look like they did indeed come from dwarf galaxies. And that was the subject of Ilona Kosovakova's senior project. She was looking at calculating orbits for these stars and figuring out where they likely originated. All right, so those are some of the really cool things that my students are doing at San Francisco State. I want to take some time to briefly talk about globular star clusters. So in my opinion, globular star clusters are the prettiest objects in the universe. They look beautiful, obviously, but they are also mysterious and interesting. So this is an example of a globular cluster taken with the Hubble Space Telescope. And we see this, it's a centrally concentrated blob of stars. In the Milky Way, many of the globular clusters sort of live in the outer regions in this spherical distribution of stars, what we call the halo. And that's different from the disk, what we normally think of as the Milky Way, which is where the sun lives. Many of these clusters are also old. All of the sort of classical clusters, globular clusters, are old. Simulations say that globular clusters should form during really intense periods of star formation. And so because they're old, because they're sort of in the halo, they're pervasive throughout the galaxy, they likely formed during intense star formation. This means that they really probably probe early star formation or accretion into the Milky Way. So they're a really important component to how the Milky Way has formed. But we're talking about the R process tonight. So what do globular clusters have to do with the R process? Well, most, and maybe even all of them, are enhanced, or at least moderately enhanced, in the R process. So if you look at a star within a globular cluster, you would classify it as an R1 or an R2 star. So that's interesting because it says that because these clusters are old, the R process has to happen very early on, and because there's a lot of clusters throughout the galaxy, the R process has to happen everywhere, very early on, which is interesting. But then this cluster in particular, M15, is even more unusual because it has a spread within the cluster of these R process elements. So if you look at one star, it will have a different abundance of barium or europium from another star. And that's really weird because that's not something you see in the other globular clusters. And so that was the subject of my first master's student, Jonathan Cabrera Garcia's thesis. He's now a PhD student at Notre Dame, and he looked at 63 stars in this cluster and to characterize the spread, and he is almost finished with this paper, which should be out soon. But the important thing is that this shows that a neutron star merger or a jet supernova, whatever it was that created the R process, had to happen while the cluster was forming, which is kind of weird and unusual because there are some important timing constraints here. All right, so just to conclude those three portions of the talk, barium and europium are really useful elements for understanding the R process. The R process alliance is increasing the number of known R process enhanced metal poor stars, and that data that we're getting is providing really important constraints on the site or sites of R process nucleosynthesis, as well as the assembly history of the Milky Way. Globular clusters are a really important piece of this puzzle, and we're doing lots of really cool stuff at San Francisco State. To conclude, I would like to come back to Earth and talk about our place in the universe, because I've been talking about stars that are thousands of light years away, but of course all of this data was taken on Earth, and astronomy is deeply connected with the Earth. And that's why I'm part of an organization called Astronomers for Planet Earth that was founded at San Francisco State and Yale in 2019. We are a group of professional astronomers, students, educators, K through 12 higher ed educators, people who work in planetariums, museums, science writers, anyone who has a connection to astronomy. And we are focused on bringing the astronomical perspective to climate change and really using astronomy as a tool to do something about it. And so you may think, like, what do astronomers have to bring to this discussion? Well, remember that we talked about the formation of spectra in stars and using this information to determine the chemical compositions of stars. Well, the same thing actually happens on Earth, right? Earth has an atmosphere. Earth produces radiation from the surface. It's infrared radiation, but it's still radiation. And that radiation is absorbed by the carbon dioxide in the atmosphere or other greenhouse gases. It's a very similar process. And there are other people, of course, who study the atmospheres of planets as well, other astronomers. So, we have expertise in understanding atmospheres, the chemical composition, the spectra, radiation, all of these things. We have a lot of expertise in this. We understand the Earth's connection with the sun and the solar cycle and things like that. We can talk about Earth in an astronomical context, in comparisons with Venus or Mars and the greenhouse effects they've experienced and how that's different from Earth. But also, we can talk about Earth in comparison with planets beyond our solar system, the exoplanets. We can also mention that it is impossible to travel to those planets, right? So we don't have a way of escaping the situation on Earth. And of course, we are also physicists, and so we understand a lot of the physics of climate change, and as well, even more importantly, climate change solutions, and many more applications. And I just highlight this because if you're interested in learning more about the astronomical perspective on climate change, you can visit our website, astronomersforplanet.earth, easy to remember. You can also follow us on social media. But I do want to highlight that we have fabulous videos on Vimeo and YouTube, and I've been highlighting a lot of the work of my students, and I want to particularly highlight Jessica Agnos again, one of my master's students, because she and her husband, Steve Agnos, have been responsible for making several very fantastic videos, and in particular, one is called A Brave and Startling Truth, which is set to a poem by Maya Angelou, and it's really powerful. So I encourage you to please check those out. And with that, I look forward to your questions. So thank you for staying this long, and I hope you're all awake. Yeah. All right, questions? Yes.
Some globular clusters show two different turnoff points, suggesting two different ages. Does that correlate strongly with the metallicity patterns that you're seeing? Do you see significant metallicity patterns in two turnoff clusters, like 1 for 1? Mm-hmm. Or are they loosely coupled?
So most globular clusters don't have a significant age spread. There are some that do, and they also have spreads in iron as well as other elements. And so, you know, they're sort of less relevant for this discussion because there's a lot going on there. But like this cluster, M15, doesn't have a significant age spread. And there are spreads in other elements like sodium and oxygen, but they are not related or not correlated with the spread in barium and europium. So it's a different cause, basically. Yeah.